for the speaker. Sarah, when Luigi comes, he comes typically with 2 logins and he needs to be co-host on both of them. One is his computer and one is his laptop. So once he's here, we should do that.
Okay, so let me summarize what we did. The last thing that we did last time, I was looking at, say, an aggregate that is growing, if you want, in a free fluid, and I was showing this difference between, this is the aggregate when you have a certain law that starts like a straight line in sigma, and this is with a parabola. You just have this boundary that is moving at a finite speed that, say, in some sense, identifies the border of the tumor. What I will do now is to go a step forward and to see what happens if you then add, say, the growth of a tissue in another tissue. Okay, the difference in some sense is minor because you will find T is the tumor, H is the host. You find the same equation. The difference between the two, of course, the first one that you will see is this one, is the growth term in tumor tissue. I'm using a logistic growth, a logistic term, and then later on I will comment on how this again can be related to a mechanical effect, an effect of stress on growth. The second, say, difference that you have to look for is the fact that, of course, the motilities of the cells can be different, and also the response to compression will be different. Okay? So at this point, you have a tumor inside, if you want. Omega T is the domain of the tumor, and a tissue outside, and you have to give some interface conditions. The natural interface conditions to pose are the continuity of stresses, in the sense that the two tissue exchange forces. Okay, so you have sigma T and sigma H in the two is equal, which means, by the way, that if they behave in the same way in both tissue, if you want, if the sigma is the same, this implies the continuity of the density of the volume ratio. But if this is different, then you will have a discontinuity in your density, in your volume ratio. The second one is a continuity of flux. I mean, a continuity, if you want, of normal velocity, because I remember that the velocity at which the cell will move is the one inside the divergence without the term Pt, without the state variable. Okay? So this is the velocity, Bt, and this is the velocity, Bh, and you are assuming that the normal component of the velocity is equal. And since this border is a border of a tumor, so it's advancing with the velocity of the tumor cells, or if you want, which is the same, with the velocity of the host cell, then this term here will also govern, say, how the interface is advancing in time. Okay? So this is the model that you can work. So let's look at what happens in one-dimensional problems. So this is the inside of a tumor. Initially, you have everything at 0.5 till, say, what, 0.01 or 0.02. Then it is growing, and it's advancing. You have the frontier. So this graph is very similar to the other one. But now we have an outside that, of course, will be compressed. You see here that it's compressed by the tumor that is growing. The outside tissue is not growing nor dying, nor dying. It's in homeostatic condition. And this, you can compare this with this cartoon made by biologists, in which you have a tumor mass that is proliferating in some sense more than normal, and this will compress the tissue outside. If you look at the overall quantity, and I stress that here the motility is the same, and also the stress volume ratio function is the same, then you just have a very smooth, say, solution And in order to distinguish between the two cells, you only to have to say that you can only color the inside and the outside like it is done here. The blue one are the bad one, and the white and the green one are the good guys. But now what happens if you change the motility? This is a case, oh, sorry, no, before that. What happens if you increase the motility? Okay? If you increase the motility, if as you expect, okay, okay, the tissue, growing tissue will expand more rapidly. And after all, if the motility is very high, you have a solution that is almost constant. If you remind some model that we already discussed in that sense at the beginning, one can assume that the motility, the density of the cell inside the tissue is more or less constant, doesn't change much. And this is the case. In fact, you find many models that assume that the density of the tumor is constant. This is achieved here, for instance, by either changing the motility term or changing the slope of the function sigma. It is from the thicker line you go to the thinner line, you increase the slope. Okay, good. And so the question is, what is the relationship between these models that I was describing, in which you have the velocity in terms of the stress, and the one in which you have the velocity is just related to the gradient of a potential? This is an assumption that is usually done. It's called, I call it potential flow assumption. Most of them call it Darcy's law. And you don't have, as you can see in the first equation, the derivative of the volume ratio, because this is assumed to be constantly equal to T0. Well, you can do that in a naive way. I mean, in some sense, you can, let's see if I have that, you can do this expansion. You can say that the volume ratio is basically a constant plus a small perturbation, while your sigma as a slope that is very large. Okay? So this is the slope of this straight line, if you want. The tangent here is P0, and the slope is sigma 0 over epsilon. So if you do that, and you substitute into the equation, on the right-hand side, you have epsilon, the P1 over T, and on the right-hand side, two first order, you only get something that is constant. This sigma prime 0 is constant, plus the growth term, or if you want, this thing here. Okay? By, say, playing with the variable and defining this psi m sigma prime m sigma prime 0 p1. Okay, this is it. So the relationship with this constant volume models and say the model in which I take into account of the variability, but the stiffness, or in the same way the motility are very high, is this one. Okay, it's just an expansion, and this was done in a, say, formal way by the group of Benoit Pertin that used this relationship within sigma and phi, this one, phi to the beta, and they let beta to infinity. When the exponent goes to infinity, you have, say, for beta over 2, you have a parabola. Instead, when beta is 100, it's very flat here, and then steepen up. Okay? And in the limit, it can be proved that this problem on the top becomes this one on the bottom. And the most important thing is that you have that the solution satisfies either sigma equal to 0, which is this region here in the limit, that is P can be anything, or PC equal to 1. That is the volume ratio is constant to 1. Okay, this is the statement of the problem. If C is less than 1, then the stress is equal to 0. You are in what can be called a non-confluent situation. Nothing is moved, is moving because sigma is equal to 0, so the gradient is equal to 0. And the evolution equation is just an equation in which you don't have any divergence. It's this equation. If instead you are in the other case, sigma c equal to 1, then the equation that governs sigma is a Laplace equation, like take the divergence of the gradient of sigma c infinity, and you have a growth term. Okay? So after all, the picture is the following. Okay? This is what happens. You might have certain region in which, say, the volume ratio, the non-confluent region in which the volume ratio is less than 1. Then in this white region, the volume ratio is 1, constant. So it means that are compressed. This C is different than 1, then different than 0, built up, and satisfies well, psi c and sigma c infinity is the same thing. And you can have any solution in the gray region. While in the white region, you have the constant value for the volume ratio. Okay, good. Now, what is most striking and interesting probably is what happens when you have the different motility. Okay, this is the case in which the motility inside, say, is smaller than the motility outside, 1 order of magnitude less. It means that in this case you lose the continuity of the derivative. You have a discontinuous derivative at the border, and it's expanding. Fine. Instead, if you have the inside is very motile, at the end of the story, in the tumor, you have a solution that is almost flat, and the tissue is compressing outside, like on the picture on the right. Okay? This is not really interesting. Probably the most interesting thing is what happens when you go to two-dimensional problems, okay, or three-dimensional problems. So I hope that it will start soon. Let's see. To show up, or I have to go back and recover that. Okay. This is a solution in 2D. When the tumor is in some sense soft, is less motile. So, well, this is not really interesting if you want. Uh, the interesting thing happens when you have the next slide. You have instead a more motile tumor penetrating the less motile tissue. Okay, and you have this one. So you expect, in some sense, that the tumor border, which is flat, so this is a one-dimensional, if you want, problem in principle, remains flat. But this is not the case, because the flat solution is unstable and it fingers. Okay, you have the growth of some fingering, and you can probably compare this picture here with what you see in a vertical section of this thin tumor, in which you have these digits, these fingers that go inside the tissue. And the same thing occurs in, say, in a spherical situation. Oh no, oh, sorry, I and you have this. You see, the sphere, the expanding sphere, is no longer a sphere because it becomes unstable, and you have this instability. From the physical point of view, this instability is well known. It is called Hirschel instability, and there are also some physical experiments that show that uh, the principle is more or less the same, in the sense that you are injecting in this case, more viscous fluid, a less viscous fluid. So if you want, the more viscous fluid is less motile, and the more viscous fluid is more motile. And you have the formation of this, say, fingers. This actually almost fractal structure. Okay,
Luigi, Luigi,
you might then compare that with one of the known features of malignity or melanomas that has to do with the border of the melanoma. Okay, if the border is compact, then everything is fine. If it is is wavy, then it is a say sign of that you might need some autopsy and see what it is. Okay.
Luigi, Luigi is Thomas. Luigi,
Yes.
in your simulations, what do we see? So the black outline is the free boundary, and the colors in yellow to blue, what is that?
Is the density.
Of
Is the
what?
density of say tumor in the host.
Oh, I see, the total density.
The total, yeah, it's the total density, but inside, say, the border, of course, you have tumor inside. Yeah, here you have tumor, okay, and here you have host. So
I see.
inside is, if you want, PT, and outside is pH.
Thank you.
Okay. Okay. Other mathematical features they come into play is the following. To make an example, if I have, in this case, I'm not considering a segregated situation. In the previous case, I had tumors inside and host outside. But I have, say, that the two cell types are mixed. They are co-present, if you want, right? They occupy the same space. So in this case, this velocity here, these terms, in particular the stress, depends on the sum of the two volume ratio. What I mean is that if you are in a bus, in a crowded bus, okay, and you feel, say, compressed by the other people, you don't actually discriminate whether the other is a male or a female, a child or an elderly guy, and so on. Okay? What is important is the total volume that is occupied, the total density of the thing. So if you want, PT is one subpopulation, PH is the other subpopulation, but they move because of the, say, total density, total volume ratio of all the population. So this gives to the set of diffusion equation a structure that is called cross diffusion. You see that you find here the same operator on the first and on the second equation. Okay? This is some particular feature because, for instance, if you have a solution, any say distribution of PT and a distribution of pH which is complementary to a constant, so it's C bar, some constant minus pH of X, this is an equilibrium, okay? Because, you know, the gradient of the sum of the two is just the gradient of a constant and nothing moves. So the solution can be any distribution of Ptn plus pH. Okay, this is one of the general features. The other one is that summing up the two, and this is I already did something like that. Summing up the two, you have an equation for the total, say, volume ratio. This one. This is parabolic. You have derivative of c of psi respect to time and here you have the second derivative with respect to space, and that's okay. And playing with, say, the equations, I can find out a second equation for another, in some sense, peculiar state variable. In order to do that, I will just expand this divergence, okay? I will, for sake of space, I will call V sake of space, but also sake of generality. I will call V all the V, all the things that are in V. So I will just say split this divergence of Pt in V scalar gradient of Pt minus Pt the divergence of V, okay? And then I will divide by Pt. If I divide by Vt, then here I have the same divergence of V. So if I subtract them, these terms drop. And so what you have is an equation for this quantity. You have this one, the one in the black, in the red box. So you have 1 over Pt, the time derivative of Pt over T, and so on, equal to minus V, the scalar of the same thing. Okay, more or less the same thing. So if you define key, the logarithm of Pt over Ph, you have an equation for this key that is not a diffusion equation. It's a transport equation. So at the end of this story, this system of two equations that looks like a system of parabolic equations is not a system of parabolic equations, because one equation is parabolic and the other one is hyperbolic. Okay? Because it has only one derivative in the space variable multiplied by a velocity, which is the one here that depends on the variable. Okay? And this gives you a lot of interesting features when you go to simulations, like the one of the existence of trons and compensation of one population by the other according to the coefficient. Okay, let's go to another feature of these models. I already discussed a bit this case, the cohesive case, in which you don't have a sigma that is non-decreasing anywhere. I mean, it's always increasing or is flat. But in the cohesive case, you have a region in which the derivative of sigma is negative. Okay? And this is bad because at the end of the story, it might give blow up of the solution, actually instability of the solution that they it's called instability, it's called Hadamard instability. To tell you the truth, has some sense because if I go back to the picture, okay, what happens here is that as soon as two cells succeed in touching each other, they will try to merge and to make a little island, leaving some space between the island. Okay, and qualitatively, this is what happens. If you have a density that is too small, you have the cells are just living away from each other in a non-confluent situation. If you reach a certain density, then you get this clustering here. Okay, so from the simulation point of view, what I will show here is a graph in which you start, for instance, from the blue distribution, just a bell shape. Point two is this point here. So, sorry, is this point here. This is point two. So as long as you are in this region, there is no velocity. So every cell will duplicate in a non-confluent, in a pure situation without moving. Okay, and you have this raising up. As soon as you reach point two, then you have this clustering. So you have the development, mathematically speaking, of this instability that going up and down, really very widely. Okay? In order to get to a good situation, you have to reach say, in this case was 0.6, and this was okay. Okay, and so this is so this is something that you have to take care of if you have this cohesive, say, stress volume ratio relationship or this cohesive situation. One way to go around with this problem is to say introduce a bilaplasian in the operator. This is done, so write a Caniliard equation after all. And the deduction of this equation is the following. I mean, this is the mass balance equation that Tc over T equal to the divergence of J. And before I had that this J, this flux, is just some coefficient times the gradient of phi. Okay? Or the gradient of some function of phi, sigma. We call it sigma. Instead, in the Caniliard models, what you say is that this quantity in the gradient is the derivative of some energy which has a potential, okay, plus some term that depends on the gradient of Pc. And this takes into account of non-local effect in the original derivation of the Canadian relation. Okay, so if you do that and you compute the functional derivative here, you end up with an equation which is the old one. The first term is the old one, but you see that you have a bi-Laplacian because you have the divergence of a gradient of a Laplacian with a minus sign, which means that even if this u prime is negative, so it gives rise to unstable situation, this one might stabilize this term, and in particular, it will stabilize the short waves, okay, especially the short wave system. So what I cannot tell you more about that. What is done here, the important thing is the choice of u, of this function u, okay? And the feature of this function u is to have two minima, okay? So that you can discriminate, say, a region in which one has, say, the solution that is close to, in this case, phi equals 0, and a region in which the solution is close to phi equal 1. So phi equals 0 corresponds, for instance, to a host situation, and 1 to a tumor region. And you have a transition from this 0, 1 that is smooth, and the thickness of the transition is just this epsilon here. Okay, this is so epsilon is the thickness of the smooth transition from the tumor and host situation. It's not a sharp interface as we showed in the previous slide. So this is the easiest one. This is the easiest potential that you can use. Another one that is often used is this one, okay, that has the characteristic to have infinite slope at 0 and 1. This is introduced because, as I mentioned at the beginning, you want to be sure that your solution, your state variable, is between 0 and 1. The first choice will not assure you that. The second one will, exactly because for the fact that the time derivative goes to infinity, you see at this slope, this is an asymptotic. Asymptotically goes to minus infinity and to plus infinity. This will avoid the solution to stay beyond 0 and 1. In this case, these are just a cubic function, and this there is no asymptote in 0 or 1, or even to say minus 0.4. It's not working properly. So if you look at the solution in this case, and this was done by Chatelain, Charlet, and Benamar, you have that this is the border of an advancing, say, tumor with time, and this spontaneously again forms this wave structure because the border again is unstable to long way. Okay, and this is the simulation in say in a 2D case. 2D case. This is of course this is also 2D, but it's a frame. This starts from a sphere, and you have a sphere that is advancing a circular plane in space. Okay, again, in some sense, this is another situation. The experiment is the following. You have two clones of some colon cancer cells. Okay, this one on the left is more motile. This one on the right is less motile. They live in a gel in the experiment, okay, with a certain say stiffness, and you see with time that this clone grows more than this one. Okay, so at the end of the story, you have three components in this model: the population one, the one on the left, population on the right, and the gel in the environment. Actually, in the simulation here there is a third host population, and this is what you see. Okay, at the end, when you grow and you look at the volume ratio, okay, this is the border of one. You will see the other one growing. Okay, this is the volume ratio. You see that on the left, the color is almost homogeneous with respect to the one on the right, because on the right, since cells are not so motile, then they will be more compressed. Okay, they will not be able to release the stress so easily. Okay, then as time goes by, you will see that also the clone on the left will be compressed. Okay, both because it becomes larger and larger, and because this one on the right is pushing, and then, but it's still more motile, and after all, the clone on the left more or less will engulf the one on the right. Okay. In this case, the law that I give for the growth term has to do with the stress. It's related to stress in the sense that when the cells are stressed, they duplicate less. This is a well-known phenomenon which is called contact inhibition of growth. I jumped that part, but I will leave you the slides for those who are interested in looking some details in this phenomenon. So if you look at the growth rates, so in some sense I'm plotting the right-hand side in the mass balance equation. At the beginning, you see that both clones are proliferating a lot. Okay, then this one in the center is not proliferating, not because of nutrient, because in this experiment the simulation is 2D and the nutrient comes from above. Okay, so all cells and all the nutrient available. It's just the lack of space that inhibits their duplication, the compression felt by the other cells. So they don't duplicate. You see, they are more or less Chan. Okay, Chan means 0. Then if you go on, also the one on the right, when they come into contact, proliferate less. But still, if you look at the proliferating rim, the red stuff, the proliferating rim of the less motile clone, has a smaller thickness depth than the one on the left. So this one on the left will proliferate faster, and this is the reason why, after all, the clone on the left will engulf the one on the right. So this is the second aspect in which contact growth, stress is important. It's the fact that it governs in many cases, at least influences in many cases, the proliferation of cells. And in fact, this is the experiment that is done usually. This is the original experiment, one of the first ones done by Nate, Jane, and so on, more or less 40 years ago. Okay, they did the following: they placed some spheres, a spheroid uh, of a certain diameter, more or less 20 microns, something like that. Yeah, 20 microns. So very few cells, I would say, in a gel with different stiffness. So the first graph that you see on the top is just growth in a liquid environment, so free of stress, and no one is compressing the cell. The other ones are compressed in a gel with increasing stiffness from top to bottom. This means that when the cells are growing, they are, of course, displacing the gel. The gel is an elastic material which will then respond to this compression, applying a stress on the cells. Okay? And you see that all of them will, at the end, eventually tend to a, say, limit radius. Okay? This is another classical feature of this growth. And the growth will start more or less when this radius is between, say, 100, say, 1/10 of a millimeter and 1 millimeter. The other feature of this experiment is if you take a spheroid like this one, for instance, and you take it out of the gel and you leave it grow in a liquid environment, so stress-free, then they start duplicating air. So, I mean, this process is reversible. And you see then that the only difference between this behavior on the left and this one on the right is that you are not applying any longer any stress to the tumor. So, today, there is a similar experiments, but done in a more, say, controllable environment, which involves, say, the application of pressure by osmosis, an osmotic pressure. It is the cells are grown in a solution with dextran. Dextran is a big molecule. It cannot penetrate into the spheroid, and so this difference in concentration will generate a compression of the spheroid. And the main difference between these experiments and the other one is that in this case the compression is constant, the stress applied to the spheroid is constant, while in the other one, of course, as you increase the radius of the spheroid, as the radius of the spheroid increases, the stress applied to the spheroid is increasing. Okay, so it's a bit more difficult in some sense to simulate. It can be done, however. It can be done. So this is what you see in the experiments. You have to look at the dots, at the big dots here, and you have that regardless of how many stairs you put at the beginning, 1,000, 5,000, or 10,000, you have this growth up to an asymptotic value. Okay? And by the way, if you shift this curve to the right, all this curve end up more or less on the same master curve. Okay? When we showed that to the biologist was very surprised, but this is something that we all know from a mathematical point of view. In the sense that, in some sense, this is a solution of the spheroid radius with respect to time. It is a solution of an ODE, if you want, or a PD. If the solution is unique, then you find a unique solution. What I mean is that if you start from this clone with a 1,000 cell, and you end up with the solution when it has, say, 10,000 cells here, or you start with 10,000 cells, then you will always, say, prolongate the solution, the same solution. So that's why they have to, say, end up into the same trajectory, the same graph. Okay? Okay, at this point, I can play with the growth law and see which one is the one that is fitting better the data that I have. So this is the growth term. The idea is that this depends, of course, on the nutrient. This N is the nutrient. In this case, I have to take care of the nutrient because this is a spheroid. A nutrient will come from the outside and is consumed in the inside while perfusing inside the spheroid by a diffusion, reaction diffusion equation, a standard one, in which you have a diffusion and the absorption by the cells of this concentration of nutrient, oxygen, and glucose in general. So this first term tells you that you have duplication if the nutrients is above a critical value. This is just a normalizing factor. Okay? If the nutrient is above this critical value, then cell will trigger the proliferation. Otherwise, this is zero, and the cell will go to apoptosis. Not to apoptosis. They will stay in homeostasis. Okay? Then the second one tells you that this is a function of the stress, so the growth rate depends on the stress that the cell feels. Okay? And the stress is a function of the volume ratio, as I mentioned last time and also at the beginning of the video. So this is what you have when you apply a linear law, okay, of this type. Some constant 1 minus delta 1 times the level of stress. Okay? Is this one? And you can see that in some sense you can fit some of the lines, others, the one in the middle, cannot be fit. So you might need to modify a bit this function here, and in some sense, for instance, using a Michaelis-Menten form, you have a better fit. So this is just the same model that I showed you before for the spheroid with a growth term, that a term that depends on the nutrient diffusion and a term that depends on the stress. Okay. Now another key point that is very interesting, at least for me, is to understand how to handle a situation in which the tumor pass through membranes. This is an important step in the development of tumors because it discriminates, say, a good situation by a bad situation. What I mean is that if you look at the breast on the top, the carcinoma, say, starts, the cancer starts inside the duct of the breast, usually, or the acini where the milk is produced. And as long as they stay inside the membrane that contains this acini, is good because the surgeon can go there and eliminate just the acini if you want. You are pretty safe that there are no cells anywhere in the tissue. But if you are in a situation in which some cells have escaped this membrane, or even the membrane is ruptured, then you have you can find tumors everywhere in the breast. And for instance, in the ovary, there is another important point because there is another membrane. It's not really membrane. It's a layer of cells called mesothelial layer, and the cells start from the ovary. They pass through the membrane confining the ovary. They end up into the mesothelial space, and they adhere to the mesothelial layer. And again, if you are in this first stage, you just operate, the surgeon will eliminate everything, and it's okay. But as soon as this cells will be able to pass the mesothelial layer, or in other tumors, as soon as the cells will pass through the membranes to the cell wall, the endothelial lining of the blood vessel or the lymphatic system, you will find metastasis anywhere. And so this is very, very bad. Okay? So this is a crucial step. So in order to understand how this works, you have to look at how cell behaves in a confined environment where you have a lot of extracellular matrix. And so this is one situation that I will show. Okay, so this is a cell in this network of fibers. You see that the cells would like to go to the left. It is not able to do that. Why? Because this yellow part here, which is the nucleus, is stuck, cannot say penetrate into the extracellular matrix. Okay. Instead, this is what happens to another cell type. Look that the gel is the same, it's completely the same. Okay. Okay. This is the one. Okay. You see, this is a cell. The red part is the nucleus, and this can crawl more or less easily into the same gel. Why? Well, because if you look at closely at the movie, at the first one, the first movie, the nucleus was always more or less spherical. It had a lot of difficulties in deforming. This one is deforming a lot. Is saying in now it's a cylinder, more or less. It's a cigar shape. So it is very deformable. And the difference between these two cells is the fact that the first one, actually the second one, is a neutrophil. Okay, so it's a cell of the immune system. The role of the cell of the immune system is to go everywhere to look for, to search for viruses, microbes, and so on, to clean everything. And so the membrane containing the nucleus and the nucleus itself is much softer, and we can deform a lot. And in fact, if you look at an ensemble of cells, this is the difference. You will see here, yes, okay. You see here the same cells, in this case it's the same cells, but two different environments. This is, in some sense, is allowing cells to move. This is not, but I will clarify what is the difference between the two cells. The difference is the following, that the former had larger holes, so the cell can crawl in these holes. The former one have smaller holes, very thin wires, and so the cell are not able to penetrate. And the same thing, I mean, the same dynamics holds also for spheroids. These are not cells, these are spheroids, and you will see that the spheroids are contained, okay, those on the right is contained by the gel. These are not cells. These are the protrusions of the cells that would like to invade. But they are not able because the nuclei that are these numbers here that you barely see at the border of the tumor, they are stuck there. Instead, in the gel on the left, the cell will invade the tissue. And the difference is the one that I told you before. Okay? Okay, good. So what I want to understand is the role of the nucleus in this migration, in this invasion, and then to transfer this information, if I can, to the continuous model that I was describing. Okay, let's skip that. Of course, I have to simplify things. This is the picture of the cell. This is the sketch done by biologists. I will simplify even more as a mathematician, and I will look at a cell cell with a spherical nucleus, initially spherical nucleus, that wants to enter a microchannel. Okay? So the idea, I don't want to enter into details, but the idea here is that in order to do that, in order to penetrate, I have to squeeze the nucleus. And to squeeze the nucleus, I have to apply some forces and I have to do some work. Okay? Because squeezing the nucleus requires some energy. Okay? And the energy required by the nucleus to be squeezed need to be smaller by the work that can actually be done by the traction forces. So, knowing something on the traction forces, I can compute the work, and this is in some sense easy, because what I know biologically is that the traction forces are exerted in a region of the, say, cell, of the cell membrane in contact with the wall, um, in the apical region. The forces are more or less constant, of the order of 10 piconewtons, is here. So I have only to compute this integral. The integral on the surface of the membrane in contact with the wall times the density of the bonds uh, of the cell, the density of the extracellular matrix, or if you want the function mass of the wall, it can be anything. Yes? Okay? Times the force that technology is possible. So in this case, in the easiest case, these are all constant that you can find out. Okay? For the work down to squeeze the nucleus, this also in some sense is not too difficult, because in principle, if someone gives you the deformation of the nucleus, say from a sphere to an ellipsoid, or to a cigar shape, or to a dumbbell, then you can compute the energy. I mean, you give a constitutive law of the behavior of the material. This one that I'm writing here is the easiest one, is the Neuquian material, that tells you that the energy is proportional to the trace of a function of B is called the Cauchy-Green strength tensor, is just F times F transpose, and then you can compute it. So I told you, I don't want to enter into details, but I want just to say that at the end of the story, what we find is the following, is that the important thing to say penetrate into the channel is that this combination of parameters that I call G has to be large enough. Okay, and this combination of parameters has to do with something that is related to traction forces. You see, density of bonds on the cell, density of, say, extracellular matrix, the magnitude of the force, and something that has to do with the nucleus stiffness. This has to be large enough. Large enough compared to what? To a function that is a function of how big is the pore with respect to how big is the nucleus. Okay? So at the end of the story, what you have is a graph that is like that. This red line here, it tells you, discriminates in this space G and this geometrical feature of your gel, a region in which the cell cannot be penetrating the gel, from a region in which they can crawl the gel, include the extracellular matrix. So, for instance, if you have a cell with some certain characteristic, they are able to pull, they have nucleus stiffness, then if the channels are too small, they will not be able to penetrate, and if the channels instead are not too small, they will be able to penetrate. But probably the most interesting part is what you realize when you look at the other side. I mean, assume that you have a regular stuff, a regular gel, a cubic-like gel, if you want, cubic lattice. Okay, and you have in some sense a population of cells, some with a soft nucleus, for instance, and some with a stiff nucleus. Then, if you have a stiff nucleus, this G is small, so you might be here in the gray region, and so they will not be able to move, as in the movie of the gel that I showed. If instead they have a soft nucleus, they will be able to. Okay, so you have in some sense, if you have a diversity of phenotype, the cells that are more aggressive, the cells that are more motile, for instance, because the traction forces are strong enough, or the nucleus becomes less stiff, they will be the one to invade the surrounding tissue. So how can I then insert that into the model that I was showing before? Okay, let me. Okay. The thing has to do with the motility tensor. Okay, because what I'm saying is that the motility tensor is, say, decreasing with the pore area. Okay, so you see here you have a graph, experimental graph of the speed with respect to cross section. Okay, and the cross section is essentially zero. Sorry, the speed is essentially zero when the cross section is this critical cross section, okay, which is called the physical limit of migration. So the first hypothesis that I can make naive is saying that the motility tensor is not just a constant as I assumed at the beginning, but is something that is linear, say, on AM, the pore radius of my gel, minus H0, and here I have the positive part of it. So this vanishes when the pore is more than the critical value. But this A0 is not constant actually, because according to what I show you, the critical size, because of the graph of this one, okay, the critical size is a function of many things. In particular, it's a function of the how big is the pore with respect to nucleus size, okay, but it's also a function of the nucleus elasticity, of the active traction of the cell can exert the ability of the cells to exert to adhere to the extracellular matrix, and so to be able to pull on the extracellular. So you see that there are a lot of variables. And so as if I insert these ingredients in my model, this is what I get. Okay, so what I will show here is a sample situation in which the growing mass, there is a mass growing in an heterogeneous environment. This ellipsoid here are just zones with higher density, or if you want, with smaller pores. So as you expect, the cells, the spheroid will grow trying to avoid this area here. Of course, they will penetrate because these are not the forbidden regions in that sense, and so they will penetrate that, but they will penetrate them more slowly. Okay, and this is what you get. So, in heterogeneity in the tissue will, of course, lead not to a spherical growth, but to a growth that is more, say, dendritic. Okay. Instead, in this case, some of the regions, some of the ellipsoids will be too tight, in the pores that are too tight, and so the cell will not be penetrating those regions. Okay, and this is just obtained by playing with the motility tensor. So, say if you want, m is larger than 0 outside the ellipsoid and is say, very small inside the ellipsoid. But the last step is has to do with the need that I was saying at the beginning, in the sense that what I really want to do is not to understand the growth of, say, a tumor in an heterogeneous environment, but to understand the growth of a tumor inside a membrane that is confining the tumor. Okay, so what I have is something inside here, an inside region, an outside region, and three, and a membrane, and two. And if you look at the typical thickness of this region and two, this is very small. Basement membranes are of the order of 1/10 of micrometer, a cell is 10 micrometers, or even by definition, cell lining. Cell linings are thick, say, one or at most two cell layers, so they are of the order of 10 microns, and instead I'm dealing with tumor masses that have a thickness, a radius that are at least, say, 1 millimeter if you want, or 1/10 of a millimeter. Okay, so what I have here in the basic problem is the continuity of stress, the continuity of velocity, of fluxes, and I want to find what is the nice and good interface condition to pose on the boundary when mathematically I replace this region that is thick with the epsilon thickness with an effective interface which does the same job. Okay, I can do that playing with the limit epsilon equals to 0. And what I find is that for this equation here, taken as an example of equation, but you can do that for any other model if you like. I mean, the methodology is the same. We just go to epsilon to go to 0, but then you have to increase, actually to decrease the permeability of this membrane, in this case, the motility inside of this membrane. And then you find out that the exact boundary interface condition to pose on this interface are the continuity of flux. And this is expected because, of course, if you have some cells that are coming out of the ovary, you will find them outside the ovary. Okay, so this has to do with mass conservation in the absence of growth. And the second one is less, say, understandable because they controls the flux of cells according to the jump of this function of the stress. So it tells you that there is a function of the stress that is relating, or of the compression. The compression is governing how many cells will go out from the region in to region out. Okay? So let me, for the sake of time, let me just quickly go to the end. So I'm applying this to the case of the ovary. I have to add a process that is called metalloproteinases, that is the cell able to produce, for instance, MLPs. MLPs are cutting the fibers so that these holes are enlarging, and enlarging this motility through the membrane can increase, and so from being completely compartmentalized, they will be able to flow out of the layer. Then when they arrive at this mesothelial lining, then they will be able to, they interfere with the cell-cell junction to another protein which is called TD157. And again, this will open up the cadherin-cadherin junction and they will pass through. So at the end of the story, this is what you get. Okay? You see at the beginning, you see a tumor contained in the ovary. Then it is degrading this part here of the membrane. It will go to the space, the mesothelial space. This is the mesothelial lining. And so at some point it will break through also the mesothelial lining and will go through. And you can appreciate that the solution across these two membranes is discontinuous. Okay? Is discontinuous because no one tells you that there is continuity of the volume ratio, the continuity is the continuity of flux, and so and if you are in the limit in which there is no permeability, you will have no passage, for instance, through mesothelial lining. You will only have, say, that the cells are contained, say, above zero, say, in the top region of this graph. And so I think I can stop here and be ready for questions.
Oh, thanks very much, Luigi. This was absolutely awesome. Um,
Let me
yeah, in
see.
particular, your ovarian simulations. I have not seen those. These are really cool. So let's have room for some quick questions. See if there are any. Yeah, if not, then so this is the end of this course of this lecture series. I really benefited from it, and I hope all the students did as well. I think we did a lot. We started with the hallmarks of cancer, and then we did some basic mathematics on dynamical systems and PDEs and traveling waves and all that. And then we saw how this was applied by many of the speakers here. Right, Natalia used this feedback mechanisms and cell lineages, and Anna Marciniak-Chokra as well. Mark Chaplin used PDEs and angiogenesis and reaction diffusion equations. Tom Yankilov started with imaging, so he used all these kind of imaging data in a very impressive way. And now Luigi looks at cells and how they extend and how they're compressed by stresses and by tissue mechanics. And this is a lot, isn't it? So if you are now, or if I would be a student hearing all this, I would be entirely confused and thinking this is way too much for one person to study.
You
And
know,
yeah,
there is
Luigi.
even more.
And this is why this is too much for one person, right? This is why we work in
Yeah,
teams. We
yeah.
work together. Yeah.
Yeah,
And
fine.
and so you should try to find your own thing. So maybe something really touched you and you thought, oh, this is really cool and this is really interesting. So I encourage you to focus on that and become an expert in whatever you thought was really cool here. So I thank all the speakers, Luigi, I thank you, and I thank all the other speakers who were here. I thank the students very much for your engaged participation, for your questions, for your comments, etc. Thanks for
Okay.
being here.
Thank you. Listen, Thomas, should I send the slides to you and the chapters to you or someone else?
Yeah, please send it to me. Yeah,
Okay, good.
yeah.
Okay,
Thank you, Luigi.
see you soon, pretty soon.
Pretty soon. Wonderful.
Huh? Bye-bye.
Bye-bye. Yeah, thank you all for coming. It was great. I had fun. And see you next time. So, PB 121.